There we go. Okay, so we'll cover diodes, bipolar, Thevenin bridge. Anything else to start with? Start there and see how it goes. All right, let's start with diodes. So what kind of diode? Just a conglomeration of them all? Okay, that's easy enough. Alrighty, I'll go to draw. Alright, so diodes. When we have them in a circuit, the schematic symbol is going to look like this. We've got our anode and our cathode. This is the negative side of the cathode, your anode is positive. When you look at them, they'll look like that, physically. So when we have those that's how they're designated with the negatives. The LEDs are a little bit easier because they have the flat. Zeners, regular ones, are all going to look like this guy. When we put them into a circuit, we have to determine if they're forward bias or if they're reverse bias. Okay? Would you guys like to run through one of the triple points problems? Okay? We'll do one of those here too. I'll add that to the list. Do what? We can. It's just they are designed to get you guys to think. So that's why I don't have a problem running through them now. All right. So in a circuit, we have to determine if it's forward or reverse bias. If a diode is in forward bias, with the exception of LEDs, what is the voltage drop? 0.7 if they're silicon. If they're not silicon, they're going to be germanium, and they're 0.3. If they're in reverse bias, it's going to be all the voltage unless it's a zener. All right, so if we have a simple circuit, like this. So we have 5 volts. With our diode in this configuration, what's going to be the voltage? So 4.3 across the resistor and 0.7 volts across our diode. Okay, we could take this out a step farther. Okay, we have this circuit. It did escalate quickly. So if we have this circuit, we want to know what's the voltage of R1, the current of R1, the voltage of R2, and the current of R2. So first off, we have to determine these diodes, are they in forward or reverse bias? D1 is forward bias. And then we'll say this one's a germanium diode. That one drops 0.3. So we know we're going to have a 0.3 volt drop here. Okay, what about the rest of our circuit? D2 will have 5 volts because zener is in reverse bias. Because they're in parallel. So we'll have 5 volts across this. So we have 0.3 there. We have 5 volts there. What do we have across R2? Okay. How much current do we have through R1? Not through R1. 50 milliamps. How much current do we have going through R2? $147 milliamps. How much current's going through our diode? 147. Okay. How much current's going through our Zener? 97. Yep. Because we have the 147 coming in, it has to split. So our diode current ends up being 97 milliamps. Okay. Pretty easy. You'll see circuits like this. Once we start getting into AC, diodes are going to become a lot more common because we use them to control it. Because there's times we don't want negative pulses to come through. We want it to turn on and then turn off. Turn on and turn off. We don't want it to turn on, reverse directions, and then turn off. Maybe we do. Maybe we have something that we want to oscillate back and forth, you know. That's really what you have going on in the fans, like the old oscillating fans. Is you got a circuit in there that turns in one direction and then turns to the next. And actually it's just got one continuous one that does it, but if you wanted to control it with the electronics and not hardware, you could build it so it would build off of the AC signal. It would speed up and slow down and then speed up and slow down going in opposite directions. Yes? With their forward bias, they drop 0.7 if they're silicon. 20 questions. There's only 20. Yeah, it's 3 hours. Mm-hmm. Be careful. It's true. Just be careful. So there's not saying that each of these questions aren't going to have, multiple parts to them. But just saying. All right, so does this make sense though? All we have to do is we have to determine if the diodes are in forward or reverse bias to start with. Once we have that, we can go through and solve the rest of the circuit. How long will it take you to pass this? Probably an hour. Double check. Yep. A lot of the time is going to be double checking. Okay. Let's apply this. To our circuit. Yes. Okay, so this is one of the triple points. So we've got 12, 9, and 5. 12 volts, 9 volts, and 5 volts. 1.1 and 3. And we got 1, 3, and 7, 5. Got 5 and 6 is 5, 1, and 1, 1. We have C1. The cool part about this Really doesn't matter what that value is. The only thing it would matter for is if we were, finding tau to figure out how long it took for the circuit to come to charge. But we're going to assume, based on this, because we're not asking, for one, we don't have our capacitance value, we're not given any times, we're going to assume that this is on and it's running. What's going to happen? So what we're looking for is the voltage for AB, which is across the capacitor, the current of AB, the VCD, which is across the diode, and the current CD. So we've got these points. Current is correct. It will have voltage. But yes, you're right. It is an open, so there will be zero current across that capacitor. All right, let's get started solving this guy. First thing we need to do is what we've talked about. What's the capacitor going to be? An open. So that's what we're going to have at this point. We will come back and we'll solve for the voltage of it, but at this point we know it's going to be an open, so we can take it out of the circuit. The next thing we need to do, take out the diode, because we need to figure out if this diode is going to be forward or reverse bias. So what we need to do is we need to go through and solve these voltages for all these different points. Okay, the biggest one really is we either need to solve for R3 and R4, because we're going to go from C to D, or we're solved backwards, R2, 1, 6, and 5. Either way, it doesn't matter, as long as we go in a complete loop from where we're going to where we want to end up, between C and D. Honestly, it's just easier to find these voltages for those two values. Okay, so the first thing we need to figure out is what is the total voltage, what is the total resistance of this circuit at this point. Okay, these two power supplies, are they series aiding, series opposing, parallel aiding, parallel opposing? Series aiding, okay? So we're going to end up with 21 volts. Our total of this circuit, all of those in series, because all of our branches are now gone. They're opens. So we have 1.1K, we've got 3K, 1.3K, 19.1. So 19.1K. Now we need to solve for the voltage drops across R3 and R4 in this configuration. Yep. So VR3 is equal to 21 volts times 1.3K divided by the 19.1K. VR4 is equal to the 21 volts times the 7.5K over the 19.1K. You'd subtract them. Yep. Because again, everything has to add up to 0. So negative 12 plus, 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 minus 9, plus, plus, plus. So R4 is going to be a little bit less than half the voltage, so a little less than 10 is my guess. Okay, there's also a reason I switched colors, because this is not going to be the final voltages of these components. Just like in Thevenin, this is a temporary placeholder for what we're solving for. So R3 is 1.429 volts, and this is 8.246 volts. Okay, so if we go from here, we're going to have polarities of positive, negative, Negative, positive across the power supply, positive, negative here. So first thing we're going to run into is a plus 1.429 minus 9 plus 8.246 volts. So what does that end up with? What do we need to have to equal 0? Positive or negative coming up from D? How much? 625? Okay. So, does everybody agree with that? Yep. It's going to drop all of that. Okay. So in this configuration, this is the voltage that we have. This guy is going to be in forward bias because we have a positive voltage on the positive. So the voltage drop of this diode is going to be 0.675 because it's forward bias. Yep. So this value is what this is going to be. These ones we're going to come back and solve. They're probably going to be close to those values again. I would imagine. Okay? But again, this guy's forward bias, so it's going to drop 0.67 as much as it can, and then the rest of the voltage would be dropped. So we're not quite fully turning this diode on. It's pretty close, and so we're going to say it's going to be the 0.675 volts. It's not going to steal any more voltage from these other guys. So we look at our mesh loops. We have A, we have B. So we know this is forward bias, we know that voltage, now we need to find these currents so we can solve for the rest of the voltages across this guy. So loop 1, we're going to end up with 12 is equal to, we got, right, yeah, we would. Do what? Well, yeah, the polarity is going to be this way, but we're assuming current is going clockwise. It probably is going to come out to where the current's going to go the other direction. Okay, so we'll write out our equation. So we got 1.1K times A plus 3K times A plus the 0.675. It'd be minus, sorry, because we have that polarity. So minus, and then we got the plus 5.1K plus the 1.1K times A equals 0. In this case, we've already solved for this voltage, so now, we don't have to worry about that, our Q, or I mean the B between those. Now we're just going to solve for what our A current is. Huh? Oh, it would be, there we go. You said what? Yep. Okay. So we've got 1.23 milliamps going there. We can then find those voltages. What do we have for current for B? Now, in this instance, we don't necessarily have to use the mesh because we know what that voltage is going to be. But we're still using Kirchhoff to solve for all these guys. Zero, 2, 3. Okay, and again, doesn't matter where we start. So we've got the plus 6.7, or sorry, plus the 0.675 volts, plus 1.3 K times B, minus 9, plus 7.5 K times B equals 0. So we're going to have a 1300 and 750. So we've got 8.8 K times B minus 8.325 equal to 0. And we get the 946.023. Okay. What value did you get? 945.978. Mm-hmm. Mm-hmm. Unless you had just a slightly different answer here. Anyway, we're good. We're within tolerance. Okay, so now that we have those, so these currents are what's going to be flowing through each of these resistors. Okay, we know the voltage across C to D. We know the current from A to B. Now we just got the last two things to figure out. How much current is going through this diode? If we have, what we got? 1.23 milliamps coming into it. And we have 946.023 microamps going out of that node. Okay, there's our current. And then the voltages, we need to solve for either R1 and R6 or R2 and R5. Again, it doesn't matter which direction we go because we want to go from point A to point B. So we either go through R1, through the source, through R6 and back, or through R2, through our diode, and back to R5. Again, like I said, it doesn't matter where we go. We have the same current. So what's the voltage that we have across R1? How much? Okay. How much voltage do we have across R6? And that's one reason to look at. Can you shorten the number of calculations? You're going to have positive to negative voltage this way. You're going to have negative to positive voltage this way. So we start at point A, we come around. So we have a negative 1.353. We have a positive 12. We have a negative 1.353. That all has to equal 0, which is what we're looking for. That's the voltage of the capacitor. Yep. And we're going to charge in that polarity. Mm-hmm. Yep. Because either way, it's going to be negative. The first thing we're going to run into is a negative. Yep. So that's the triple points. It really is that simple. There's lots of steps, but it really does come down to that simple as far as what we're doing. Yeah. Because we have 1.23 milliamps going through R2, we also have 1.23 milliamps going through R1, because how much current do we have going through C1? 0. Because it's a capacitor with DC. It's fully charged. It's going to register as an open. And this is the value that it's going to charge to. So almost 10 volts. Yeah. Yeah, so we got the 1.23 milliamps times our 1.1 k ohms gives us the 1.353 volts. It looks like a lot, like I said, it is kind of jumbled, but you got to remember, go step by step. Take the capacitor out because it's going to be open. Take the diode out. Determine what the diode is going to be at these points from C to D. If it's going to be reverse bias or forward bias, things like that. And then once you get in there, find out the current going through it, and then basically use Kirchhoff to solve the two loops. Because we don't have to use mesh, because mesh we're using it when we don't know the current values and we have the resistance values to solve for it. Here, with the diode, we don't care what the resistance of that diode is. It's going to change based on what it needs to be to maintain its voltage. Okay? It will change. And then, so again, its resistance value is kind of like an imaginary number. It's there, but we can't actively measure it. Okay? If we had the same problem, without going through all the math and everything, what would be different if our 9-volt power supply was switched? We would subtract those to start with, and then we'd go through and determine how much voltage we have. Now, what would that put our diode? Forward or reverse bias? It'd probably put it in reverse bias. If there's 5 available. If there's not, it's going to take everything it can. So then basically what we have to do then is that 5 volts, then the rest of that voltage is going to get split out across those 2 resistors, which is what we find when we go through our Kirchhoff current or Kirchhoff voltage law. So again, this one's a good one because this incorporates the capacitors. What does it do? Incorporates the diodes. How do they work? We have Kirchhoff's voltage law. We have Kirchhoff's current law. We have Ohm's law. Really, the only things we didn't solve for was power. But in this case, I'm not too worried with microamps. Yep, that'll do it. Yeah. $250 milliwatts. Yep, quarter watts. Okay, any questions about that? Like I said, these ones are kind of fun because they make you think, but they're really not that hard. The biggest thing is just understand, what do I do with the capacitor? What do I do with the diode? The capacitor is the easiest part of the whole circuit. It's an open. The diode, we have to determine if it's forward or reverse bias, and then what is my voltage? So another way that would have been cool is if we would have upped this guy to, say, 15 volts. We would have had 0.7 here, and we would have seen the rest dropped across those resistors.
So, with the diode, the voltage is basically just the ability to put a current, right?
Yes.
So, with the voltage going to T1, why is it, like, I understand that the voltage is going to there, but, like, what's that?
That voltage is just hanging out.
Oh, because it's stored in the
It's that voltage is stored in the capacitor. So if you were to take this capacitor out of the circuit, different circuit, you would have almost 10 volts that you could then use to power something else until it ran out.
Did they actually do that?
You can.
That's pretty sick.
You can have a switching circuit in here. So what it would do is it would switch between this current coming in, and then it would switch it to where it would take it and go out. You could also use it as a relay. This could be your normally closed position, and as soon as it goes to normally open, you would throw the switch and the capacitor would be then connected to an LED. Then the capacitor would discharge, and then it would trigger back, and then your relay would open back up and have it charge. So you could use it as just as an indicator. You can now have a flashing light. Obviously, this is kind of overkill for a flashing light, and there's some more stuff you'd have to add, but you could do it. Because the idea is let's hardwire everything that we can. That's the idea first semester. Second semester adds on to the same thing. Now we're going to teach you about transistors. Once we get through transistors, you're going to get into digital. Once you get into digital, now you're understanding, okay, now I'm going to program something to turn this on and off, but internally, this is what it's doing. Inside the chip, it's going through these same circuits.
Is there a reason why someone would prefer something coded in rather than hardwired in? Or like it's hardwired?
If the biggest difference is if you want it to do the same thing over and over and over again, you hardwire it.
Yeah.
It's just easier. Because if you code it, then you got a problem. You could have a potential issue with your code. This way you can troubleshoot this. You can't necessarily troubleshoot a circuit that's going bad, like the actual chip itself. This gives you replaceable options.
So hardwiring is like the go-to method of the
Yeah, it's the root method that you want to get things set up as.
The more variables, the worse chances of going wrong.
Yes.
Murphy's Law is real.
Especially in programming.
Yeah.
It sucks, and I'm not trying to scare you or anything, but there's going to be times. The biggest culprit you're going to have in programming is the friggin' semicolon. That thing is a POS. Spaces, not so much. The software we have now are able to parse those out pretty good. But you get either an extra semicolon in somewhere, like you meant to put in a colon and you put in a semicolon. Trying to go back and look through 10,000 lines of code for a stupid semicolon is insane, and it's almost impossible.
The worst when you've been looking for like 2 hours, and you're like, hey, girl, help me out with your assignment in 3 minutes. You're just like...
It's because you get blinders on. It's your code. That's honestly the best way to fix your code is to have somebody else go through it. Because they'll look at it completely objectively. They're trying to understand it instead of what you want it to do versus what it's actually going to do. Okay. Any questions about these guys? All right. Is that also?
What was the basic steps? There's capacitor's open, take up the diode, Thevenize it.
Basically, Thevenize the diode, find out what the voltage is across there to determine if it's forward or reverse, and polarity. That's like I said, that was Thevenin. What we just did was Thevenin. We just didn't go through all the major steps that we did because we're not going to be swapping this in and out. We just wanted to know one voltage. I'm not too worried about the math stuff with you guys because everybody seems to be getting that stuff right on the tests. It's just when it comes into these problems is where the most problems erupt.
Yeah, you did like the whole, I had the line calculus, but we do like put it in there, so we have to like CYTU.
Well, it actually makes sense.
Yeah, it makes a lot more sense. I agree with that.
And here's the other thing. A lot of those degrees, the people they don't even need calculus. What they're doing. Once they want to go into calculus class, don't need what they're doing. I haven't heard any doctors doing calculus, but is there an expert?
The double bridge in parallel.
No. Stop it.
So our resistor, that J5 it looks like, that's just like protected resistor, right?
R5? Yeah, that's our shunt resistor.
Gotcha.
All right, so we've got 4321. And then B is 14 and 87.5. C is 9 and 75. Our load D is 14. And 46,667. Okay. So here's our circuit. Normally, we're going to start with bleeder. But 75. Yep. So normally we would start with finding eye bleeder, but let's take a step back and let's start solving this without the eye bleeder and see if we can determine where it needs to go. Okay? First thing we're going to do is solve our currents. So without our bleeder current to start with, let's just start going from over here on this corner. So we have point A. We've got 46.667 milliamps of current coming in. We've got 210 milliamps of current going out. Coming in. Okay, we know current is going this direction on the rest of these guys. Okay, any questions with A? Any issues with figuring that out? Okay, point B, we've got 87.5 leaving. We've got 163.333 milli leaving, and we've got 75 milli coming in. Coming in? Again, just using Kirchhoff's current law. The amount of current going into a node has to equal the current leaving the node. Okay? Now we're going to look at these values. So looking at this, which one would we expect to see our bleeder current? R3 or R2? R2. Because if we look at this guy, we have current coming in, current leaving. More likely than not, this is going to be our bleeder current. Bleeder never touches the load. Yeah. Yep. But not even to that. I just was going to show that we could figure it out without looking at that. Just working our way back, we're going to have current that's coming up here. Any current that's in this spot has never touched the load. If this was coming in and then it has to turn this way, we would get current from these guys coming back this direction. So this one has to be it because it's the only place that we're going to have current that does not ever go through the load. Okay? So now we figure out what is our bleeder current. So we've got 210 and 87.5. We're going to take 10% of that. We weren't specifically told, but if it's not told, we assume 10%. So now, at point C, if we have 29.75 milli leaving, 175.833 milli leaving, how much current do we have coming into that node through R3? Point what? 583 milliamps. Okay, we move down one node. We've got 205.5 milliamps leaving and 75 milliamps leaving. How much do we have to have coming in? Okay, coming in. And then we go down to our next node, which is point E. And honestly, you can label these as any point you want, doesn't matter. Point E, we've got 280 going in, out. We've got 667 going out. How much do we have to have coming in and going through R5? Which is our I total. Okay? .25. Okay, so again, we've got 29.75 milli coming in, 87.5 milli coming in. We have 117.25 milli going out. We have 210 milli coming out, or coming in from load A. We got 117. And they match. That's the biggest thing. This one and this one down here should match. You can assume that, but just like I said, double check your work. Because if something happened in here and you dropped a decimal, this could be wrong. And if that's the case, your answers aren't going to be right. And the cool thing is we would build this circuit, and really, we would check this voltage, we would check this current, and if those two are right, the rest of the circuit's going to work fine. So it makes it really easy. Okay? How are we going to build this guy? What voltage do we have across R1? 7 volts. How much voltage do we have across R2? 14 volts. How much voltage across R3? 9 volts. How much across 4? 5 volts. And how much across R5? 8 volts. Because again, R3 is in parallel with C. They're going to have the same voltage. 3 and 4 are in series, which are in parallel with the 14 with load D. They're going to subtract out from each other. And then the same with R2 is in parallel with load B. R1 is in series with R2, which is in parallel with load A. Those are going to have the combined voltage of that guy. We add A and B together, A and D together, subtract that from our source, and the rest of it has to be dropped across 5. They're pretty easy. The hardest part, honestly, are these two currents. Because you have to determine their value and their direction, and those ones are key. If those ones are wrong, the rest of the circuit will flop. And I would say probably over half the time, this is where people make their mistakes, are those two currents. I mean, look at this. We've done some diode work. We did a triple point, and we've done a bipolar in how long have we been recording? 46 minutes. Granted, we're all working together, but just the thing is, like, look how much you guys have learned. Like, this is what's cool. The hardest part for you guys, like I said, is going to be doing the bipolars. It's going to go through some of the Thevenin. It's going to go through some of the universal shunt meters, things like that. But you guys have the basic understanding of how electronics work, and this is what's cool. Next week, we're just going to continue on with this. We're going to take a step back and go back to the basics, but we're going to go through them pretty fast. Just we're going to be dealing with AC current versus DC current. So we'll start off with the capacitors in AC. Then we're going to move the week after that is resistors and capacitors. Week after that is resistors and inductors. Week after that we start talking about frequency response and resonance. And then that's week 4. And what? Yeah, week 4 is rough. I'm going to be honest. Week 4 is rough. Yes. Just fair warning. It's going to be rough. Because once we start getting into RLC circuits, we got several different types of filters. We got high pass, low pass, band stop, and we can make them every which way in configuration. Do what? But just so you guys know, but like I said, we're going to step you guys through this, so it's not going to be like, okay, solve this, and you have no idea what's going on. We will build up to it. The week after that, we will start getting into, week 5 is AC-DC, I believe. So we now have AC signals coupled with DC signals. Now we can change those on how they react. The week after that, week 6, I believe we start getting into power supplies. And honestly, those ones are the funnest. Your power supply will be your final, yes. AC circuit theory for fall. Yeah, it's like I said, week 1 is series capacitors. Week 2 is AC circuits. RC circuits. 3 is RL circuits. Week 4 is resonance and filters. Week 5 is AC-DC and clippers. Week 7 is the different kinds of power supplies. Or week 6, and then week 7 is clampers and or power supplies. Clamper, it shifts your signal up or down like a lot, but it uses capacitors to do it. Also that week, so that's also our final or our dead week. So that's going to be a lot of just review. I'm not going to introduce a whole lot because we're going to be done on that Wednesday. And then you have Thanksgiving, and then when you come back, or you won't come back, the week after that will be finals online. So. January 13th-ish, I believe. Let me look. Oops. Yes. So like I said, so we have the fall recess starting on November 25th. That's the Wednesday before Thanksgiving. You'll have Thanksgiving break all the way through till the 29th. And then the 30th is when we start final exams. Again, we won't be meeting in class like we are here. So what I will do is I will have a Zoom meeting opened up during our normal theory time, because I will still be here. For you guys to log in and can review. We'll just do it online, kind of in the same manner as what I've been doing. Is you'll ask questions, and I'll be drawing out on OneNote just like what we would normally. So we have that option, and then that end week will be your final, and then you have winter break until January 11th. Dang, it's 2 days off. But January 11th is the first day back. Hopefully you guys are all moving on to second semester. And then, and then spring break, like we said, is April 26th through the 30th. The week after that is finals. And then you're done for the summer. Yep. First year, first decade of college. But just so you guys know, like I said, I want you guys to be aware of what's going on. I don't want to give you surprises for that kind of stuff, but that's the plan. So, with that, let's go ahead and go to break.